Alright, so this is a problem with two masses connected by a massless frictionless pulley, and there's no friction in the problem, so we have to try to figure out what's going on. If you haven't already worked this problem yourself, then I recommend you do so before I get started. Alright, so I'm going to start off by developing this diagram into a free body diagram. So looking at the forces on mass A, I've got gravity, which points down, and I got a tension force that points up. That's it. For mass B, I've got gravity that points down, which is mBg, and so that's going to have a perpendicular component and a parallel component. The parallel component there is going to be mg sine 65, right, because that angle there is 65 degrees. And then the perpendicular component is going to be mg cosine 65 degrees. I've also got a tension force acting on mass B, which is the same as the tension force acting on mass A, and I got a normal force. And again, this is a frictionless incline, so I don't have to worry about friction. Let's see. We're told that block B moves a distance up the incline, so the direction of motion is going to be up the incline. So I'm going to make that my positive direction, right? In my sign convention, I'm going to make up the ramp positive and out of the ramp positive. And that means that over here, for mass A, the direction of motion is down. Therefore, following the same sign convention, for mass A, down is going to be positive. Right? And if we need it, then that way it would be positive. Okay, so I've established my motion, I've established all the forces that are present, and I've established my sign convention. So now I'm ready to work the problem. Again, if you haven't already worked this problem using one method or the other, then you should pause the video and work it. I'm going to start by using a force method. So let's start with mass A. For mass A, we've got the sum of all y forces is equal to gravity minus tension. Right? Notice that gravity has a positive value here because it points down, right? And tension has a negative value because it points up, and that's consistent with my sign convention over here. And then, of course, the acceleration is positive because it points up. Alright, for mass B, let me just look at the forces that are parallel to the ramp. That would be positive tension minus the parallel component of gravity, which is mg sine 65. That's equal to mba. Alright, so now I've got two equations and two unknowns. My unknowns are the acceleration and the tension force. So the way to solve a system like this is to solve for one of your unknowns. So I'm going to take this top equation here. I'm going to solve for tension. Tension is equal to MAG minus MAA. And I'm going to take that solution for equation 1 and I'm going to plug it into equation 2. That gives me this equation, which I can simplify. Well, you may not think this is simplified, but I do. Okay, so that tells me that the forces, the combined forces on all the mass is equal to the combined mass times the acceleration. Now, I want you to notice that this is we've done this sort of problem in class before. This is the same sort of problem as though I had two masses on a flat plane, right? If I had, let's say, MA here and MB here, and I had MAG pulling this way, and MBG sine 65 pointing that way, and then a rope connecting them with the tension in the middle. And my sign convention were that the direction of motion to the right were positive. If I take these two masses A and B and I treat them as one giant mass, which has a mass of MA plus MB, then the sum of the forces acting on it is plus MAG minus MBG sine 65 is equal to the combined mass times the acceleration. So this is the same problem. Anyway, so taking this equation and plugging in the numbers for what I know, there's MAG, here's MBG sine 65, that's equal to the combined mass 13 times A, so that gives me an acceleration of 1.896 meters per second squared. Right, now it wants to know the final velocity of the system, so I can solve that using my equations, my basically chapter 2 methods. I am given that delta S is positive 1.5 meters. Right? We've decided that up the incline is positive, and for mass B, and down is positive for mass A. The initial speed that starts at rest, final velocity is unknown, acceleration 1.896. Right? So I would use this equation, the equation that doesn't have time in it, to solve for V. And if I do that, I get V squared is 5.688, and so V is plus or minus 2.4 meters per second, and I'll take the positive value of that. There's my answer. So that's how to do it using the force method. If you want to solve this using chapter 5 methods, then okay, we can do that. So with chapter 5 methods, we look at all of the works done in the problem. There are 5 forces in the problem. Right? There's the force of gravity on mass A. There's the force of tension on mass A. There's the force of tension on mass B. There's the normal force on mass B. And then there's the force of gravity on mass B. Okay, so the work done by gravity on mass A is equal to the force of gravity times the displacement times the cosine of the angle between them, right? In this case, that's cosine 0, because the force of gravity and the displacement are in the same direction. So that's 110.25. The work done by tension on mass A is equal to the force of tension times delta S times the cosine of 180, because the tension and the displacement point in opposite directions, so that's minus Ft delta S. For mass B, the work done by tension is the force of tension times delta S times cosine 0, because in mass B's case, the tension and the motion are in the same direction, so that's plus Ft delta S. The normal force, of course, does no work. And then the work done by gravity for mass B can be solved in a variety of ways. You know, maybe the easiest way is to use the potential energy method. When, in this case, it's minus mgh, because it goes up, so there's the minus sign. And of course, h, the height through which it moves, is delta S sine 65. Right, because if we have a triangle where this is delta S going up the ramp, and that angle is 65 degrees, then the height, h, through which it goes is going to be delta S sine 65. Okay, and that's that's minus 73.3. Okay, so if I add up the works done by all the forces, of course, minus Ft delta S and plus Ft delta S, those go away, and so I'm left with just 36.98. And that's equal to the change in kinetic energy, which is the combined mass, 1/2 times the combined masses times v squared minus 0, because it starts at rest. And so I get 5.688 equals v squared Therefore, the final velocity is 2.4 meters per second as above. So either one of these methods work. This is one of those problems where you can use either method.